We will on Wednesday, so if it doesn't take us our whole time to finish up chapter 3 and you feel like you need to get that time out, you can hang around and we can talk some more about chapter 3. All right, so as we begin, I want to share you, it's not really a story like it was on Friday. It's more of like something that bothers me. So I am a very cynical person. I don't know if that's come off yet, but I tend to, my default is when you tell me something to assume that you're lying until it's proven otherwise. It's something I'm working on. I'm trying to trust people better, but people just keep disappointing me and making me trust some words. And you're like, wow, that's so horrible. What a horrible way to live. It's just the reality. Okay, so I'm sorry. That's who I am. So when I see food labels, I know the laws required for food labels. I don't know if you knew this or not. This may ruin your life. But you do not actually have to be 0 calorie to label something as 0 calorie. I don't know if you knew that or not, but the law will allow you to label something 0 calorie as long as you're under a certain threshold. Okay? And the same thing, you can label something gluten-free even if it is not actually gluten-free, as long as, again, it's under some threshold. Okay? And so I know this, so food labels, they just kind of bother me. And then, like, you know, there's just something attractive about gluten-free. So, like, this company, like Podunk Water Company, it's like they're not selling enough bottles of water, so they'll slap gluten-free right on top of that. And then all of a sudden, bam, it's the most popular bottle of water that there is, right? And so, you know, restaurants, you know this, restaurants are starting to do this. And I want you to know that I was a little upset when I saw that Chipotle is now offering a keto burrito bowl. And it's no different than every burrito bowl that they've ever offered. You don't get the beans, you don't get the tortilla, and it's I mean, this is the same thing. But you all know, I don't know if you remember this or not, but they had that viral outbreak, I don't know, maybe 3 or 4 years ago that was tied to Chipotle. And man, they've been working hard to try to bring that thing back. So when they slapped, like, they started advertising this keto burrito bowl, I want you to know, like, I struggled through it, and it hurt me. It hurt me deep inside. So I want you to know that so you can remember it every time you see something like that, to know that I'm struggling. And if you could pray for me, that'd be great. Because I'll tell you what, like, I am a mediocre human being when I am in a great mood. And when I'm in a bad mood, man, it's tough. It's tough for everyone around me. So you can pray for them, pray for me. All right. So we have, I think, 3 questions. All we did was carbohydrates, right? We did, like, introduction to biomolecules, and then we did carbohydrates. So we need to do lipids, we need to do proteins, we need to do nucleic acids. And so the question, how are lipids used? So of all of our biomolecules, lipids are the only ones that don't form what we call macromolecules, right? You know, we can take an individual glucose, or an individual monosaccharide sugar, and we can string a bunch of them together, right? And we do, as glycogen or starch or chitin. Proteins, you'll see this in a minute. You can take an individual amino acid and you can string thousands of them together and build something that's really big. Same thing with nucleic acid. I don't know if you knew this or not, but there is 6.5 feet of DNA in every single one of your cells. That's a lot. That is a lot of DNA. These are massive molecules. Lipids, we can't string enough lipids together really to make these into macromolecules. Okay? So lipids, of all of them, they tend to be not always the smallest, but as a group, these are the smallest of our macromolecules. But man, are they energy dense. Okay? So one of the uses of lipids is to store and release energy. Of all of the biomolecule types, carbohydrates, lipids, proteins, nucleic acids, lipids pack the most energy per unit mass, which is why if you look at on like a nutrition label, it'll tend to tell you calories, and then it'll tell you calories from fat. And the real reason why they started doing that is because in the 1980s and 1990s, there was like the only way you're going to lose weight is if you do a low-fat diet. That's it. That's all there is. And so there was all these things that were labeling themselves non-fat or fat-free. And again, they weren't really fat-free. They were just under a certain threshold. Anyways, it's another story for another time. But fats are super energy dense. Okay, it's almost 20 calories per gram. And so it's way more than protein, than carbohydrates, than nucleic acids. All of those can be used for energy. And so these are really energy dense, which is why fats are so wonderful, right? They keep you fuller longer because they're super energy dense, and it takes your body a while to break them down because they don't mix well with water. It's got to emulsify them first. And so there's just a lot of really wonderful things about fats. And this is why the main way we store energy for long-term storage is as fat and not as a glucose polymer, as glycogen. In between meals, if you go 6 hours in between meals, which that's a long time. Like, why on earth would I go 6 hours in between meals? I mean, maybe you want to sleep. And so the glycogen store in your liver is not going to even last anywhere close to that long. Okay, you're going to be through all of your sugar you have saved up way before you eat again, but then you've got these long-term storage molecules, and the best way to store it is as fat, which is why it's one of the first things to change about your body when you're consuming way more calories than you should be, is you start noticing fat deposits building up around your body. Anyways, another story for another time. All right, so lipids can also be structural. Just like carbohydrates, we can use it for energy. They can also be structural. Lipids can be structural. We find this in cell membranes. Next week, we'll do actually this week. This is already next week. This week, we'll do 40,000 feet view of the cell. And then next week, I think we'll start talking about cell membranes, and you'll see this more next week. So we'll leave that discussion for then. On top of that, lipids can be used to send signals. Many of the hormones that our bodies make to regulate function in some other part of your body are done by hormones that'll be pumped into your blood, carried around the body, and trigger some response somewhere else. A lot of those are lipids. And based on what I've already mentioned about lipids, why would lipids make such a wonderful material to do that with? Yeah. Yeah, they don't dissolve well. And so it's very difficult for them to be broken down. And if you want to send a signal a long distance, you don't want it to be broken down, right? And for it to dissolve and for it to, what's the term I'm looking for? When something becomes less concentrated.
Dilute.
What's that? No, not diffuse. Dilute. Thank you. Another D word. Yeah, those are usually the words I can't come up with. I don't know how many of you I've told this story, but I was teaching a class one time, and I could not think of the word tree. And so I'm trying to describe what I mean, and everybody, I could see people sitting there, they're like, he can't honestly be struggling to think of the word tree. And I was, and finally somebody was like, it's not a tree, is it? And I said, exactly what it is. Thank you. So it's usually those simple words. And then finally, a great way or a great use of lipids is because they don't interact well with water, they're a great way to prevent water loss. You coat an external covering with lipids, and water doesn't interact well with it, so it creates like a watertight barrier, okay? Which is one of the reasons why our skin is oily, okay? To prevent water loss. It's just wonderful. It's also why parasite eggs have a layer of oil inside of them. And so water can't penetrate into the eggs, and they almost live forever. You're like, that's so cool, because most parasites, I mean, I don't know if you know this, but I know this, I'm going to share it with you. Their transmission route is called fecal-oral, meaning you have to consume something contaminated with eggs from the feces of somebody else that was infected. And you're like, wow, I don't usually interact with people's feces, so I'm good. But then it's like, no, these eggs will survive forever. And so you could just be minding your own business, pulling weeds in your front yard, and just somebody had, for some reason, used night soil to fertilize their yard, which night soil is human feces, by the way. and you're just pulling weeds, minding your own business. You don't wash your hands well enough. And now you get infected by a parasite that was from not the last person that lived in your house, but like 3 people ago. And you're like, wow, this is just wonderful. This is how all these things work. All right. So here's a triglyceride. This is the most common form of fat that we store up for long-term energy storage. What kind of a reaction is this? A dehydration or condensation reaction, where we are forming water as a product. Look at that down there. Here's our arrow, and here's water as a product. And so we're attaching these fatty acids to this glycerol backbone for long-term storage. And so if you're going to access the energy from here, you have to go in and you have to break these bonds using what kind of reaction? A hydrolysis, where you cut with water and then start breaking these fatty acids down. Okay? And knowing that these don't interact well with water, you know that's going to be challenging, which makes it to where they don't accidentally get broken down. You need to actually deliberately start pulling from these energy reserves. Wonderful, wonderful design. And so when you're looking at these, we have basically 2 different types of long-chain fatty acids. 2 different types. One in where we have no carbon-carbon double bonds. All of the carbons are bound to basically hydrogens, and maybe they might be bound to 2 other carbons, but only 1 bond each. Okay, so all of these there aren't any carbon-carbon double bonds. You get a nice straight fatty acid. Okay, these are called saturated fatty acids because they are saturated with what? Hydrogen. They have as much hydrogen as you could pack into this hydrocarbon. They are saturated with hydrogen, and they're nice and straight. Okay, and then we look at this, and here we have a carbon-carbon double bond. So these 2 carbons sitting right next to each other are actually sharing 4 electrons instead of 2. And so now that carbon can't be, this carbon is attached to 1 less hydrogen, right? Because instead of sharing 2 electrons with a hydrogen, it's sharing 2 more with this carbon. This carbon's also attached to 1 less hydrogen, right? And so what happens here is not just that we're not holding as much hydrogen as you can pack in here. You're like, oh, that's sad. It needs more hydrogen. But it also creates a kink. And so you get basically two different forms of this. You can have the cis double bond, where both big bulky elements are on the same side, or you can have a trans double bond, where the 2 sides are on opposite sides, but the cis one creates a kink. And so instead of being a nice straight line, this one is kinked, and so you can't pack these in as tightly as you can these, right? Does that kind of make sense? You're like, okay, I got this. When I'm trying to put clothes away, they work really nicely when they're folded. They don't work so nicely when they're all messed up. You're like, I don't know that. I don't put my clothes away. I just dump the laundry basket out on my roommate's bed and slowly take the clothes I need, right? They sleep on the floor. It's this little brother situation, right? And so these are what you find in... these bonds are what you find in like animal fats that are saturated fats. And again, in the 80s and 90s, you would hear saturated fat and people would, oh, it's terrible. You can't eat animal fat. It's so bad for you. But since these can pack really tightly at room temperature, animal fats are solid, packed in nice and tight, like butter, right? Butter nice and solid, or bacon fat when it's at room temperature, nice and solid. And then you heat it up and it becomes liquid. Right? And then it just becomes something you drape over everything else, and it's delicious, right? Now, I don't like broccoli unless it's covered with butter or bacon fat. And then it's just basically a spoon to get that fat into. These are like oils that are liquid at room temperature. You can't pack them in as tightly so they don't solidify at room temperature, like olive oil or vegetable oil or peanut oil, which is obviously the king of oils. Olive oil is the queen of oils, but peanut oil, that's the king of oils. Sorry. If you don't know what I mean, fry something in peanut oil. Like, man, I had a meal with the king. And it was nice. It was nice. All right. So Yeah, something we have to bring up if you're going to talk about fats, and we're talking about that fats don't mix well with water, and the blood is basically 50% water by volume. It means you can actually, if you're not regularly using these fats, so you know if you've got too many of them or your activity rate isn't high enough, you can get these fats kind of clumping up together because again they don't mix well with water, and you can get what are called atherosclerotic plaques, where you just have basically fat globules building up and concentrating in particular areas. So fat's a great way to store energy, great way to access energy. You just got to use them. You got to use them. If you're going to build it, you use it. Like a bear, right? Bears get really fat in the fall, but then they go and sit in a cave all winter and they don't eat anything, and they use it. It's why you're most likely to be attacked by a bear in the fall, when they're building up fat reserves for the winter, and you just look delicious. Or in the spring if you happen to cross a mama with her cubs, you know. That's actually probably the most common. Oh, I've got a story, but I'll save it. So here's a phospholipid. We've got the same glycerol backbone that we saw in triglycerides, but now we've got 2 fatty acids attached to them instead of 3, and in this third spot we attach a phosphate group, which is why we call these phospholipids, because it's a lipid with a phosphate group, a phospholipid. And what it creates is actually here, especially with this polar unit here, you see polar, you think what? You think brothers, right? Uneven sharing of electrons. Or bear, that works too. It's like, why did the bear dissolve in the puddle? It was a polar bear, of course. No, but we've got a polar unit here. You think that uneven sharing of electrons, right? This is going to interact well with water, because water's polar. Right? Remember we went through all of those wonderful things about water and said they're wonderful because they're polar? So now we've got a region of this lipid that interacts well with water and a region that doesn't interact well with water, and you have something that's really wonderful. But we'll save that for next week, and we'll talk about why that is so wonderful. And then here are some of those hormones. Estradiol, a type of estrogen, and testosterone, these hormones that are just wonderful. Again, they don't dilute in the blood, so you basically get every single one of them sticking around long enough until they can have their intended effect. Okay. So I want to share you the story, and then we're going to take a lecture break. So, talking about being attacked by bears. And if it bothers you that I think this is a funny story, I'm sorry. But we would go to Mammoth in the winter time, or not in the winter, sorry, in the springtime every year when I was in high school. Because it's a really inexpensive time to go to Mammoth, because like nobody's there skiing, right? The snow's gone, and it's not yet summer when a lot of mountain bikers come, because it's an inexpensive time to go to Mammoth. But it's also a time when the mama black bears have baby black bears, and it gets a little interesting. And so we went one year, and my dad, my brother, and I were out fishing, and a baby black bear shows up and takes all of our fish. And like it wasn't, I mean, it was a pretty small black bear, but I'm like, I'm not gonna, I mean, it can have my fish. Like, I don't want to get, you know, bitten by this little black bear. But what I was more afraid of was mama bear showing up, right? Because you see baby black bear, you're like, mama bear is gonna be, so we packed our stuff up and we left. Because we didn't want to get, anyways, get mauled by a female black bear. And so we came back there later, and this baby black bear's up in a tree, and we're talking to the ranger, and he's like, yeah, its mom had been hit by a car and killed, and so it's just surviving, basically eating stuff from people that are around. And my mom's like, that is horrible. We should take care of this black bear. And so she goes to the car and grabs a sandwich. And she's like, I'm going to take care of this black bear. And the ranger's like, ma'am, put the sandwich away. But the black bear, it saw the sandwich, and it starts coming out of the tree. And so now my mom's like, man, I'm going to get this bear the sandwich. And the ranger's like yelling at her, like, ma'am, put the sandwich away. And she's like, come here, black bear. I'm going to take care of you. And so the black bear comes down, and then finally my mom's like, wow, this is probably not that great of an idea. But she's already got this black bear down, and then so she takes the sandwich and puts it behind her back. Oh, no. And so the black bear walks up to her and just looks at her and just takes its claw and slashes her leg and then runs away. And so my mom's got these 3 big gashes on her leg from this baby black bear and a sandwich behind her back, and she's just like this. And then, so like my little brother, he's like, is it okay to eat that sandwich? Oh man, that was a great story. All right, so lecture break time. So here's what I want you to do. So I want you to think about this. I told you lipids don't mix well with water. But in order to access those, we need to figure out a way to make them mix with water, right? Because our bodies are predominantly water. We've got to make it happen. So what I want you to do is take a little bit of time, maybe a minute, minute and a half with those around you, and I want you to come up with a way in which we can get fats or lipids more generally to interact with water. What's it going to take? What is it going to take to make that happen? All right? Take about a minute, minute and a half, see if you can come up with some ideas that we can use to explain this whole situation.
So in order to use yeah. That makes sense, yeah. My question is it react or interact with like breaking down fatty acids so that it can do more energy, or like what you were saying, kind of like
You got about another 30 seconds or so.
oh, you might be right. Because this reminds me of you know, you got the hydrophobic right here and the hydrophilic. I don't know how it breaks it down. Like that's what I was trying to think about. How does it use the lipids for, you know, how does it break it down? We know it breaks it down for that one says.
All right. So we've got this situation here. We've got this water, very polar, right? Water's about as polar of a molecule as you can get. Oxygen, you know, oxygen, that's a big time electron hog. We know hydrogen, it's not really. So that oxygen, man, they are just spending a whole lot of time with those shared electrons. So it's about as polar as you can get. And then we've got these. And what are these? What do these look like? They look like squids, but squids aren't like a box like this. So it's like it's a box jellyfish, but they don't look like this either. This looks like a triglyceride. Here's our glycerol, right? Here's our glycerol, and here's our 3 fatty acid tails formed by what type of reaction? How do we attach the tails to glycerol? Condensation or dehydration reaction where water is a product. How do we remove the fatty acids from the glycerol? Hydrolysis reaction, okay? We've got these. These are nonpolar. So they're going to interact with other nonpolar molecules, and they are not going to interact with these polar water molecules. It's why Italian dressing separates into the water-soluble layer and the oil unless you mix it up. You're like, okay, well, if we're going to get these to interact, we can mix it up, right? You take somebody that's got some fat in their blood and you grab them and you shake them real hard, and then we can mix them up. You're like, I got this. That's what happens, right? That's not what happens. So how do we do this? How do we get these to interact, Tara? Okay, so enzymes. The enzymes are water-soluble as well, and that's why they work well in this water environment. So they're hanging out there. I mean, there are enzymes that will break this down, but this has to get into that water-soluble layer first. Levi.
Depolarizing the triglycerides.
Okay. Depolarizing. So these aren't polarized. So let's polarize. That's an interesting thought. And we're like, let's make them share their electrons unevenly. How would you do that? We could do that by hitting them with electricity and pumping extra electrons into it. And you're like, that's so cool. That's totally what happens, right? Just take a person, they've got these fats building up in their blood. You you know, you give them a piece of foil and tell them to stick it into like an electric socket, give them a nice little shock. You could totally do that. We could do that. But that doesn't sound good. I mean, it sounds fun to watch, but not so good. You're like, does that mean if I get it struck by lightning that I'm going to break down more fat than I would otherwise? Man, maybe I should go jogging in a thunderstorm. Like, why am I living in California? Let's move to Missouri. Actually, I think Arkansas has the highest density. No, it's Florida. Florida has the highest density of thunderstorms in the U.S. The most bolts that actually hit the ground. But there's a place in Argentina that gets a lightning bolt that hits it like every 6 minutes. Yeah. There's something weird happening there where a lightning bolt hits this area like every 6 minutes, but it's up in a really high elevation. It's not a great place to live, not even just because of the lightning. Okay, so I presented to you a lipid that had a polar region and a nonpolar region, right? Do you remember what that was? It was a phospholipid, but there are other lipids like that as well that have a polar region and a nonpolar region. And so we take some of these, what we call them, I always use the wrong term, amphipathic is the term. I always want to say amphoteric, but that means something completely different. You take something that's amphipathic. Amphipathic. And amphi means like amphibious, something that works in the water and on land, like a frog, an amphibian, or an amphibious craft, right? Like a tank that drives underwater and then pops up onto the shore. Sweet. But these are amphipathic. They fear both polar and nonpolar materials. It's kind of a cool little name for them. But anyways, you take something in here that's amphipathic that has something like this, where it's got a polar end that can interact with water, and it has a nonpolar end that can interact with the triglyceride. And now this can take these things that were all clumped together and mix them all up. Mix it all up. This is what soap does. It's like if you're using antibacterial soap, it also has an antibacteria that'll kill bacteria. But the main reason why you use soap is because the oils that are on your skin, they're not going to interact well with water. So if you want to wash those off and whatever's stuck in those oils, you need something like soap that is amphipathic that will interact with the oil on your skin and with the water and will wash that away. And then your body will make more oil and it'll be fine. But if you wash your hands too often, they don't make oil fast enough and you lose too much water and your hands dry out. Right? You ever notice that if you wash your hands too often, your hands start to dry out and then they crack and bleed? Your kids are like, oh my gosh, Dad, what's wrong? Do you need a Band-Aid? Like, no, I don't need a Band-Aid. I'm a grown man. Sorry. This literally happens every single day with my daughter. So I did a little snapshot. Dad, your hand's bleeding. Do you need a Band-Aid? Sorry. Okay, so does this make sense? This is how we get fats or oils or nonpolar materials to interact with water. We use something that's amphipathic. This process is called emulsifying. And so you use that same term in cooking if you want to mix your oil and your water-soluble materials together so that your sauce doesn't break. Have you ever heard the term like the sauce was broken? It means that your fats and your water-soluble layers are separated. They're no longer emulsified and mixed together. And it's kind of unpleasant to eat because then it's just really oily. But when it's not broken, you see this a lot with like a hollandaise sauce, which is delicious, probably the best sauce ever made. But when it breaks, it's not that enjoyable. I don't know if you knew this or not, but hollandaise is a mixture of egg yolk and some acid. Usually lemon juice, but it can be vinegar or passion fruit juice, really whatever you want to use. Pineapple juice, make it a little bit sweeter, right? So then you can put your hollandaise sauce on cake instead of just on, an egg. Sorry. All right. Okay. Any questions here? Yeah, Chris.
What are some of those amphipathic?
Yeah, detergents are amphipathic. So there's a general term to refer to a lot of these things as detergents. And then biosalts that are made by your gallbladder, or really they're concentrated in your gallbladder, they're made in your liver, are these and will emulsify the fats. And that's why if somebody has to have their gallbladder removed, they usually have a hard time digesting really fatty food because they can't concentrate those bile salts in between meals, and they don't make enough to keep up with demand, and they can't kind of accumulate them. Yeah?
What's the difference between the antipathic and the surfactant?
That's a good question. Surfactant, I believe, is like an engineering term used for the same thing.
Okay.
Like, so a surfactant is like an amphipathic material used to accomplish some task, I think is how it works, but you'd have to ask an engineer. Is your dad an engineer? Your older brother? Yeah, you'd have to ask an engineer. All right. Why are proteins so important? So, oh wait, are there any questions on lipids? Okay, so proteins. Proteins are polymers of amino acids bound in what's called a peptide bond. But if we're going to link different monomers up together, what type of reaction are we going to use? Condensation or dehydration, where water is a product. Now, fully functional proteins have to have the correct three-dimensional shape. It's not about just having all the right amino acids. It also needs to be shaped exactly right. We call that the tertiary structure. This root tertiary means what? Third level. So you're like, well, what's the primary and the secondary structure? Glad you asked. We'll get there. And then you're like, is there anything beyond tertiary? We'll get there too. Now, individual amino acids, these can be used to release energy. Which is why, like, in prolonged periods of starvation, if you've moved through your fat reserves, you'll start hydrolyzing proteins in your muscle tissue. And you'll start losing muscle mass. Okay, because your body will start breaking down those proteins to access individual amino acids. The amino acids come in different chemical varieties. There are a lot of different types of amino acids. There are 20 of them that are found in living tissue. 20 amino acids found in living tissue. That's a good number to keep in mind. I don't think it's written on the slide. It's a good number to keep in mind, 20 amino acids. Now, proteins do much of the work of the cell. So there are proteins that act as enzymes that carry out these reactions. Tara, you were talking about these. There are certainly enzymes that are going to facilitate breaking these fatty acid tails off the glycerol. There are enzymes that are going to facilitate breaking those fatty acids down into individual pieces. There are proteins that work as transport molecules to carry things around inside of the cell. There are proteins that work as regulatory molecules that control what the cell does and how much of particular products it makes. Some of our hormones are proteins. And you're like, okay, well, those are going to be broken down more quickly than hormones that are what? Lipids. So these are hormones that you don't want sticking around in the blood for a long time. Okay? That you want to go into the blood to get an immediate response and then to get broken down and disappear. Versus if you want something that you need prolonged response to, probably want to use a lipid for that hormone. And then proteins that can act as receptors to grab things on the cell surface. Proteins can also be structural. We find this in the cytoskeleton of the cell. Do you know what this root cyto means? It means cell. And so this is the cell skeleton. It's so wonderful. What about cytostome? Do you know what that means? The root stome is mouth. It's a cell mouth. You're like, what is that? We'll get there. And then proteins can function to actually move cells. We have different types of proteins that do these. Some that make flagella, which is basically like a single spaghetti noodle that whips around and propels something through the water. Cilia, which is the same structure, but there's a whole bunch of these, and they function almost like little hands just kind of flapping the cell through the water. And then pseudopodia, these to grow the cell out in a particular area. Those are kind of fun. Do you know what this root pseudo means? It means fake or false. And what this means? Foot, like a podiatrist. This is a fake foot. And it's so cool because when you actually watch a cell moving like this, it looks like it's just like sticking its foot out and then the whole cell moves in that direction. It's fun to watch. And then proteins kind of become a scaffolding that a lot of other things attach to. So we get lipoproteins that are lipids mixed with protein. We get glycoproteins that are sugars mixed with proteins. and we get nucleoproteins that are nucleic acids mixed with proteins. And so proteins are, if you're going to use the analogy of a factory for a cell, have you ever seen something like that? The analogy of a factory is kind of fun. The proteins are all of the materials necessary to build whatever that factory is producing. They're all the workers in the factory and all of the machinery. It's all protein. You're like, well, that's so cool. What do the other things do? It's a wonderful question. The lipids, they're kind of like the walls of the factory. The nucleic acids, they're the white-collar workers, right? The people with the fancy jobs, but they don't actually do anything, right? And then the sugars, the things that make everybody happy, right? They're the glue that holds everything together. Oh, man, that was good. That was good. All right. So, here it is, the 20 different amino acids. It is there. Just wasn't on that slide. 20 different amino acids found in living tissues. And you need all 20 of those amino acids. Some of them you cannot make yourself. You cannot make them. Meaning the only place to get them is where? In your diet, in your food, as you break down proteins from what you eat. So here's the general formula of an amino acid. What functional group is this? This is an amine group. What functional group is this? Carboxyl group. So we've got both an amine group and a carboxyl group here. A carboxyl group acts as an acid. So this is an amino acid. Look at that. The name actually means something. And then this R, we know what that R is, right? Some hydrocarbon. Okay, but it actually could be something other than a hydrocarbon, but it just is some carbon-containing materials. You can have something more than just carbons and hydrogens. But that's the only place where the different amino acids differ. So all 20 amino acids, they look the same here, and then this R group is different. Any questions about this so far? Yeah, Levi.
What did you say the COH?
It's a carboxyl group is the functional group, but it's an acid. And so that's where the name of these come, an amino acid. All right. What type of a reaction are we going to use to string amino acids together? Dehydration or condensation, where water is a product. Okay, well look at this. We've got an OH that we can take off here, and we've got a hydrogen that we can take off here to make our water, right? 1 oxygen and 2 hydrogen. So if you're going to string these amino acids together, we're probably going to string something, attach another one here. And look at this. Here are 2 amino acids, and here's that carboxyl group written out, and here's the amino group, and look at these. They'll form a bond here, and you'll get water as a product, and we've made a new bond. Now we call it a peptide bond in these, and the reason why we call it a peptide bond is because another name for protein is what? A polypeptide. You ever heard that before used to refer to a protein? And so that's why we call it a peptide bond. All right. Okay, so we need primary and secondary, right? We know that the tertiary structure of a protein is what? Is its three-dimensional shape. The primary structure is just the sequence of amino acids. So we have 20 different amino acids. Here's serine, glutamine, glycine, aspartate, tryptophan. Oh, what is GLN? It's not glutamate, that's GLM. I don't know. Leucine, histine. Histine? Is that right? Histamine? I don't know. Whatever. Doesn't matter at this point. But we can string these, the order of amino acids. That's the primary structure of a protein. The secondary structure of a protein is when we start to form some regional three-dimensional shapes. Like in this one, we're getting what's called an alpha helix. We're getting a helix that forms, which is basically a tunnel. Some regional three-dimensional shapes. And then our tertiary is now the overall three-dimensional structure. That's cool, right? So we've got several different helices, and then there are other types of regional three-dimensional structures as well. So now we know primary. Primary is the amino acid sequence. We know secondary, that's regional three-dimensionality. We know tertiary, that's the overall three-dimensional shape. Is there anything else? And the answer is yes. There's quaternary, and this is where it ends. It doesn't go any further than that, because what would you even call it if it was a fifth level? I don't even know. Pentiary? I don't know. But we've got quaternary structure. This is if you need multiple proteins to attach together to carry out some task. So this right here, what is this? Beta globin, alpha globin. Many of you wrote about this in your response to the question number 5. On your actually, it's question 6, because questions 1 through 4 are matching. Number 5 is multiple choice. It's a hemoglobin. We've got a heme and we've got a globin. A heme and a globin. What do you get? It's hemoglobin, and what does it do? Carries oxygen. Okay, it carries oxygen in red blood cells, but it only works when you have all 4 of these proteins together. So you have 4 separate proteins that all come together to carry that out. All right, quaternary structure. I'm going to move past the next slide. We don't need to talk about it at this point. Boom, boom, there it was. There it goes. Okay. We'll talk about it more when we talk about enzymes. All right. We got one last question. We did it. We got to question number 5. It took us, how many? We have 55 minutes in each class time. 55 and 45, what is that, 100 minutes? It's 55 and 45, 100. It's Monday, so my math skills are usually pretty poor, but I'm pretty sure that's 100. It took us 100 minutes to get to somewhere where I thought we'd get to much more quickly. I talk too much, tell too many stories, but they're fun. I think y'all should, if you meet my mom and you see 3 scars on her leg, you're going to know exactly where they came from. And if you're going to see like her tendency to hide sandwiches behind her back from people, you're going to know why, you know. She has a great heart. She didn't want that bear to starve to death. All right, how do nucleic acids store information? That question's actually how do they store information and store energy? So nucleic acids are usually polymers. They're not always polymers like sugars. Right? Sugar can just be a single unit like glucose called what? What is a single sugar unit called? Monosaccharide. Or they can be a polymer of that, and then we call it what? A polysaccharide. It's so cool, right? Nucleic acids are pretty much the same way. An individual amino acid, it's not a protein. It's nothing like a protein. But with sugars and nucleic acids, you can have an individual unit, it's still a nucleic acid. Or you can have a whole string of them, it's still a nucleic acid. Just like with sugar, you can have a single unit, or you can have a whole bunch of them, and they're still sugars. Okay? So they're usually polymers of nucleotide monomers linked in a bond. Now, how do you think we're going to form this bond? What type of reaction? Dehydration or condensation. But again, like proteins, it's an important bond, so it gets its own name, a phosphodiester bond. Phospho means what's going to be part of that bond? Phosphorus, a phosphate functional group. All right. So these individual monomers are called nucleotides, and the nucleotides are made up of a sugar, could be ribose, could be deoxyribose, a phosphate group, and then this big nitrogen containing basically a lipid. And so these nucleic acids they're basically a composite of other types of organic molecules. Now, these individual monomers called nucleotides, they can be used to store energy. Have you seen ATP before? Okay, it's the currency of the cell. Every cell in your body makes, on average, 100 pounds of ATP a day. Every single cell in your body. You're like, that doesn't even make sense, because I've got trillions of cells in my body, except for they use everything they make. Every cell in your body makes 100 pounds and uses 100 pounds of ATP every single day. That's impressive. And then GTP, it's another one. It's rare. We see that. ADP is what ATP becomes when you remove a phosphate group, because you know that ATP stands for what? Adenosine triphosphate. Tri meaning 3. What do you think that D stands for? Di. Just 2 of them. Okay, look at that, critical thinking. So the monomers can be used to store energy. The polymers can be used to store information. Because you can order your nucleotides in a very specific way to convey some information. They can also be used to transport information because some of them can actually leave the nucleus. Again, nucleic acids in our factory analogy, who are they? I mentioned this to you maybe 7 minutes ago. Who are the nucleic acids? They're the white-collar workers. But some of them, they don't ever leave the office, right? They're the big wigs. Do you know where that phrase big wig comes from? It's because wigs are really expensive. And so if you could afford a big wig, you're it, you know? You're a big wig, sorry. So yeah, the DNA, those are like the really fancy white-collar workers. You don't even see them. You're the protein working in that factory, you don't even know who that person is. You've seen their name written on a piece of paper, but you've never seen them. And then you've got the other white-collar workers. They still don't do anything except for just carry the, you know, the rules from the big workers out to the workers. Yeah. That's a great analogy. It's hard to find a place where it breaks down. You know, other analogies, they break down all the time. I used one in genetics this morning that really was awful, and then I tried to make it better, and it just made it worse. I'll share that analogy with you. I'll save it for when we talk about DNA in more detail. So here's a nucleotide. Here's this sugar, either ribose or deoxyribose. What does deoxy mean? Without oxygen. Look at this. If it's got an OH there, it's ribose. If it only has an H, it's deoxyribose. Ribose without the oxygen. Man, it makes sense. It's just wonderful. And then so here we've got this nitrogen-containing base, lots of nitrogens there. And then here we've got our phosphate groups. Okay. In this one, it's adenine shown, so this is adenosine as long as it's ribose, triphosphate, ATP, which can be used to store energy, or it can be strung together like so to store information. Okay? Individual nucleotide can store energy. You string them together, now you can store information because every base is a little bit different. And so the order of bases conveys meaning as long as you can read them. Yeah, Levi.
What does base mean?
That's a good question. We just use the, because typically in science it means it's basic, right? Like it has a pH above 7. That may be where it originates, but overall, DNA is actually an acidic molecule, and so that base by itself, that base by itself might actually be basic. I don't know, but we just use the term base to refer to this portion of the nucleotide that is involved in something else, and we'll see this again in a lot more detail later on. So we're not going to talk about a lot about nucleic acids now, because we're going to spend like 3 or 4 weeks of our class talking about nucleic acids and horrible, horrible analogies for them, right? The nice thing, a good analogy makes you feel good, right? Because you're like, that's a good representation of it. A bad analogy you'll remember forever. So in some ways, bad analogies are actually better, right? Well, that's it. It's currently 12:37. We have 3 scheduled minutes of our class left. And so if you want to hang out and you want to chat, feel free. If you want to get up and leave, feel free to do that as well. Yeah. Room 22 is just that way. Yeah. So there are 2 of them, and then we'll open up the wall. Yeah.
Are we going to need like lab coats or anything for lab today? Okay.
No.
Okay. Do we need to do anything before the lab? Or that was kind of looking.